Good afternoon, everyone. I am Navanita Chakraborty from Research Section. On behalf of Research Section, I welcome you all to our today's lecture in memory of Dr. APJ Abdul Kalam. We welcome our today's speaker, Dr. Abhishek Tiwari. Dr. Tiwari joined IIT Ropar in 2020 as an assistant professor at the Department of Metallurgical and Materials Engineering. He completed his BTech from NIT Jamshedpur in 2008 and MTech from IIT Kharagpur in 2012. Dr. Tiwari is a silver medalist in his MTech program and he got his PhD from Bhabha Atomic Research Center. He has worked on the concept of configurational Dr. Tiwari has worked on the concept of configurational forces for Austrian Academy of Sciences as a postdoctoral researcher and continues to apply the configurational force concept in various fields of materials mechanics. The title of our today's talk is Configurational Forces and a Roller Coaster Ride with Crack Team. We welcome you again, Dr. Tiwari, and over to you.
Thank you very much for this nice introduction and for the platform to share the research idea. So I will share my screen now and I hope it is visible and I am audible to everyone. So I am audible to everyone, right?
Yes, yes.
Okay.
Make a full screen for his slides.
Yes. Okay, so I have already thanked for this platform and I will start my talk without any further ado. The talk is on configurational forces and how do we understand and how can we enhance the resistance of a material if there is a flaw in the material. And before we do try to understand that, the question is that why we need to understand about crack tips. So whatever components or machine we make, whether it is a small or big, for example bridges, buildings, phone or bone, everything has some structural component to it and they are prone to fracture. And so for example even semiconductors can go thermal strain and they can fail. So we need to know that when the material will fail and how much time do we have to repair it, replace it or run away from it. So this is the importance of structural integrity, and I will also share an example with you which is not too bad. A flight on April 28, 1988 takes off from Hilo Airport. And this flight used to fly to Honolulu Airport at least 10 times in a day because the distance between these two airports is very short. So it is just 350 kilometers away. So it used to hop on and off for 10 times at least. And on April 28, after 20 minutes of taking off, the upper frame of this aircraft flew away. And one of the flight attendants, who was 58 years old, she was on the verge of retirement, she was also sucked away in the sky. And this was not that fatal accident because nobody else died. So there was only one casualty. And the pilot decided to do emergency landing in the Kahului airport, which is in the middle. And he saved all of them. This is the real picture of that flight. And you can probably fathom the kind of trauma and adventure these passengers have gone through when they see the open sky in the flight. And fortunately, they were lucky because they had their seat belts on. The flight attendant was serving the passengers, so she was not having the seat belt on, and that's why that happened. There has been other casualties where nobody survived. So these are the things, not only aircraft, but the other components also, where we need to understand that if there is a flaw, what can we do about it and what are our options. And in order to understand that, we need to understand the behavior of the flaw. The fail-safe design approach assumes and accepts the idea that there will always be a flaw or more than one flaw in the system. And therefore, the fracture mechanics begins with that idea that we have a crack. So let us look at a little history of fracture mechanics. I didn't explain the mechanism why this aircraft failed. As I told you that this flight used to do frequent jumps between these two airports, which is at very short duration. And whenever a flight takes off and lands, the cabin of the aircraft goes under compression and decompression cycle to have the same atmospheric pressure which you have on ground. And this causes a cyclic loading on the body of the aircraft. Usually the cyclic loading is on the wings and on the turbine blades. Apart from cyclic, we have higher temperature in the jet engines. But in this case, the body failed, and the body failed because of the compression decompression cycle. If you look at the amount of flight hours this flight was, it was 35,500 approximately, and that is not a large amount of a huge amount of flight hours for an aircraft to fail. But in this short span of the time for which the craft was in the sky, it went through approximately 90,000 compression decompression cycles. And the add-on was the harsh environment of the sea. So you have a lot of salt and moisture in the air which assists the damage which starts because of the cyclic loading. So this is why it happened. And if we try to find out the first documentation of any experiment which is documented for the fracture of a material, we find that in the notebook of Leonardo da Vinci in 1500 century. And in this experiment we have a wire hanging, and this wire there is a bucket which is hanging with the wire, and we have an assembly where there is sand, and this sand is being poured from this small hole in the bucket. There is a big hole dug beneath this wire so that when the wire fails, this bucket with the sand will fall into it and we will not lose any of the sand. And when it fails, then we can measure the amount of sand which caused the wire to fail, and then we know the fracture stress. But fracture is a very common phenomena. So it cannot be true that it started in 1500 century. It is as common as apple falling on somebody's head, because if the head is not there, then it will fall on ground and it will fracture. But the first flaw-based analysis we find in 1913 when English uses theory of elasticity, and he uses theory of elasticity for a finite radii flaw which looks like an ellipse here. So this is the flaw in the material which has major and minor radii of B and C. And he says that if you apply a load on this structure, then the load is concentrated at the tips of this flaw. And the amount by which it will be concentrated is given by the geometry of the flaw. But so far English is talking about a flaw which is finite. So it is like a hole. It's not a crack. The usual cracks are very sharp. And the sharp cracks, this radii tends to 0. And in that case, the damage will be severe. So we need to understand what happens when there is a sharp crack. And that comes when Sir A. Griffith gives applies the law of thermodynamics in the field of fracture. So the idea is very simple, and usually ideas are very simple. It just takes somebody to think and apply it. And that's what Griffith did. And he said that we are applying some amount of energy to the system, and because of which the system is failing. And therefore, the amount of energy which we are giving in the system is going where? It is going in creation of two new surfaces. So there is a block of material and we apply load on it, and then this block of material breaks into two pieces, and therefore we have these two new surfaces which has been created. And therefore, in order to create these new surfaces, we need some amount of energy, and that amount of energy is coming by what we are applying on. And he equates it and he gets the fracture stress criteria, which is here. But we already are getting a signal of what will come in future. So if you just multiply this denominator on the left hand side, then you get something on the right hand side which is material property. So Young's modulus is a material constant, and surface energy is also a material constant. So the left hand side is telling you about a material property which will come when George Irwin starts working about it, and he started working on on fracture in 1948, and he uses Griffith's idea, and he saw that what Griffith said is not valid. So he used Griffith's equation, and it is not giving the solution. And the reason was that Griffith was working on brittle materials like glass, and George Irwin was working on, so he used to work in Navy, and so he was working on steels and cast irons, which are not as brittle as glass. So he found out that there is some amount of energy which material is eating, consuming, and it is not going to spit it out. So that energy is permanently going in the system, and he adds that plastic energy, and we will see that this plastic energy, how it causes problem in the later on solutions. So then George Irwin goes further, and he develops the stress and strain behavior for a sharp crack, which are these, and he finds that for every stress expression we get a common term. This is common in all the stress expression. Of course, there is a dependency on the angle, which is theta, but apart from that, this is common. And he calls this one, which is actually sigma root pi a, and this is what we saw as a signal in Griffith's analysis, is a stress intensity factor. It is called a stress intensity factor because by this much amount, the stress is being intensified. So, and the other important parameter is R. So when you approach closer to the crack tip, so R will be 0 somewhere here. When you go closer to the crack tip, the stress goes to infinity. That means material is taking infinite amount of load, and if that is true, then we can fight gods, because material cannot break because it is able to take infinite amount of load. But that is not true, because somewhere it will hit the plasticity. And if we assume ideal plasticity, then stress will not increase beyond yield strength. And therefore, there is a small zone, small or larger depends upon the condition, but there is a zone at the crack tip which is deforming plastically. Irwin didn't know much about how to solve the equations in the plastic zone, so he said that make sure that your plastic zone is very small, and then you can still deal with the theory of elasticity. And so that idea was standardized in the form of ASTM E399. It is also used even today for brittle materials like glasses and ceramics. And the constraint which it imposes on the specimen is that the smallest dimension of the specimen should at least be greater than 50 times of the plastic zone radius. And this causes problem for ductile materials like steel. Steel is a material which is used in the maximum amount in the structural components. And for steels, you have to test a specimen which is at least 2 feet thick, so 62.5 centimeters. And you can imagine if you have a sample which is 2 feet thick, what kind of load you will have to apply to first handle it and then break it and then handle the broken sample. So this is not so good for testing ductile materials. And then comes the revolutionary idea of James Rice, which is called J integral. And this idea was not for the first time used in fracture mechanics by James Rice, but this idea existed before in the field of gravity and in the field of electromagnetism. So the idea is, if you have a conservative field and you take the inner product of the force in the conservative field with the radial vector increment dr along a line. So imagine this blue line to be the line along which we are taking this integral. So that's a line integral, and the value will always be 0. It simply says that whatever form of energy is coming in is going out, unless there is a source or sink of energy. So if we have a source of energy, we add that term. If we have a sink of energy, we subtract that term, and then that's the equation we have. James Rice takes that and defines it as J integral, probably because his first name was James, and he uses the same thing. So here also you see the first term is the energy which is stored by the material. So W is strain energy density, which is simply the integration of stress over strain. So to the amount of strain you are deforming the material, you do the integration. So if you have stress strain diagram like this, then you simply find out this area, and that will be your strain energy density. And the second term is T is the traction vector, del u by del x is the displacement gradient, ds is the small element on this contour, and it tells that how much amount of energy you are giving to the system. So the amount of energy you are giving is stored by the material, and if there is nothing left, then this integration value will be 0. But if you have a source or sink of energy, as I said, then it will not be 0. And in this case, the singularity is the crack tip. So we have one singularity in the loop, in the contour where we are taking this integral. So we can uniquely define this singularity using this integration. Because this singularity is not changing, it is not growing. So if we take the line integral here, or if we take the line integral there, or if we take the line integral there, or if we take the line integral along this green line, we will always get same value because we only have one singularity, which is the crack tip, and that is embedded in all those line contours which we are, the value we are taking in. And that gives a very good advantage to us, that because we cannot measure anything at the crack tip, this path independence of this integration allows us to measure the properties at remote location and relate it to what is happening at the crack tip. But remember that we started with a conservative field. And in the continuum mechanics, this stress-strain behavior can only be conservative if it is elastic. So it will always follow the same path. If you load it, so if I'm loading the system, it is going in this direction, and when I'm unloading it, it will follow the same path and it will go back to 0. Because elastic deformation is reversible, so we come back to 0. But the reality is different. So in reality, if I have a material and I'm loading it, this is usually for the metallic material, this is the linear elastic part. So if I unload anywhere in this region, it will obviously go back, but after that plasticity starts. And if you unload it, then there is some amount of strain which is recovered, which is elastic strain, and some amount of strain which is not recovered, and that is plastic strain. So then it is not a conservative field. So to avoid that problem, Rice said that assume this material to be non-linear elastic. Assume it to be non-linear elastic. This works as long as we are just loading it, but it breaks down when we unload it, and that's the problem with this. So experimentally, this integration is calculated by loading a sample, and then you get force versus displacement diagram. We get force versus displacement diagram, and you take the area under this curve, which will be related to the energy consumed. So you can change force to stress and displacement to strain, and if you do that, you will get strain energy density. In this case, we are taking the area under force displacement curve, so we need a factor which is eta, and then divide by the cross section of that part of the material which is taking the load, and then you get the J integral experimentally. But the problem is that we are also counting the plastic part here. So this part. The problem here is that this part of J integral is not available for the crack tip. So if crack has to move, this energy cannot be used. This energy is permanently taken by the material, and the material will not give it back. So only this elastic energy, which is stored as a storage, and it is available. So when the crack needs to grow, it needs some amount of energy, and that energy can only come from the stored elastic energy. And we are also counting plastic energy, and that's the problem. So it is not defining crack driving force, but it is defining the material's resistance. Plastic energy is the form by which material is responding. It is fighting back to those forces which are trying to break the material. So in a nutshell, this J integral will not define the true crack driving force as long as the crack grows. So for a stationary crack, we are still loading it. We are not, there is no unloading happening. Well, in some cases there will be unloading happening, but let us assume that for small amount of deformation, as long as we are just pulling the system and crack does not grow, we are not unloading it. But if crack grows, then what happens? So imagine this specimen has initial crack length of A, and then the specimen had a little bit of increment in the crack length by an amount delta A. So the crack has grown, So what happens to the material point which is here, let's say? When it was, so this material point was initially there, and therefore it must have a high stress value, right? So that value of stress was some finite value. And now the crack has grown and that material point is no longer attached to the other point on the other side. So the stress value there is 0. This means there has been an unloading, and unloading is not allowed in this concept. Okay. And because of that,
I am in soup ना मैं कर रही हूँ उसको मैनेज बट अगली बार से थोड़ा ध्यान रखना ठीक है कोई बात नहीं हाँ ध्यान रखना अगली बार
hello?
ठीक है
Neha, can you please mute your mic? Abhishek, please go ahead.
Okay, so I was explaining that when the crack grows, there is some amount of unloading in the system, and that's where the J integral cannot define the true crack driving force. It can define something. What it defines is the resistance. What it defines is how much energy is released per unit crack growth, but that is also not true. So it doesn't define how much energy is released, but it is defining everything. It is defining the amount of energy which is released, plus it is also calculating the amount of energy which is consumed by the system in the plastic deformation. And that is where there is a problem. And now let us look at, so this is what I explained. That was the experimental part, and if we have to calculate this J integral numerically, then we can simply apply this equation in finite element analysis softwares, and we can calculate these terms like phi is strain energy density, and T is traction, and all those other terms I have already defined. So all those data you can straight away get from finite element software, and you can calculate this J integral. But because J integral assumes this material to be non-linear elastic, it takes the whole area under the stress strain curve. But only this part of an elastic plastic material is available for the crack to grow. So if you have to take it, then you should only take strain energy density or elastic strain energy density. But in that case, the definition of J integral will face a lot of problems. So the solution which we are proposing, okay, so before that we need to have something in our mind. We have talked about what is the problem with the J integral, and then let us understand this, that the amount of energy which is available at the crack tip, which is the true crack driving force, let us call that J integral. The conventional J integral is having some problems that we have discussed. This crack driving force which is available at the crack tip, if it is greater than the resistance which material is offering, then crack will grow, and if it is lower than that, then crack will not grow. This is not very hard to accept. And now okay, so now let us look at the solution. And solution is coming from the configurational forces. The name might sound very difficult or maybe not, but this idea has been applied in many other fields. In the field of fracture mechanics, this is new. The idea came long back in 1956 when Eshelby talks about energy momentum tensor, and we call that configurational stress. And what is this force? This configurational force is not new. We all know it, what kind of force it is. So for any entity, if there are two situations where that same entity can be having a stage where it is having energy which is lower, so it can have a lower energy state, then it will always try to go there. So if we have water at an elevation, then this water will always try to go to ground zero. And because of this energy difference, we will always have a force which will compel this water to go on the ground, but this cannot happen as long as I put a hole in it. If I don't put a hole, it has to be there. So there is a force on the system, but it cannot do anything because there is no path. And this force is configurational force in continuum mechanics. So if you assume an interstitial atom inside a material, I will not call this interstitial atom very sad, but it is also not in the most happiest situation because there are bigger atoms which are trying to compress this. They don't want it. They want the void to be void. And if this interstitial atom goes to the surface, at least half of the side will be compression free. So there exists a situation where this atom can be a little more happier, and therefore there will be a force on it which will compel this atom to go to the surface. Whether or not it goes to the surface depends if there is a path provided to it. And that is in a nutshell what configurational forces are. And we calculate configurational forces from the configurational stress tensor, which is also the energy momentum tensor of SLBs, and it is not very difficult. So we have strain energy density multiplied by the identity tensor, and then we have deformation gradient transpose and first Piola-Kasov stress. It is similar to J integral. The first term is the energy stored in the material, and the second term is the energy which is provided to the material. And if you take a divergence of this term, then divergence of any property tells you about the inwardness or outwardness of that. And if the divergence of that value is 0, it means the property is neither inward, it's not showing inwardness or outwardness, so there is a balance. If there is a balance, then there is no force. If there is no balance, then there is a force, and that force is configurational force. And for different situations, like at crack tip and at surface, the terms in the equation changes a little bit, but the basic idea is in this equation. And if you compare it with the J integral, it is same. Advantage here is that we have not assumed anything about the material or the loading type. So we are not saying that the material has to be elastic, non-linear elastic. The material can be deforming in any way, and there can be unloading, there can be creep deformation, and therefore this concept is valid under any type of deformation: creep, viscoelasticity, elastic, plastic, or completely elastic. So this is how we calculate configurational forces in finite element analysis. And then we sum it over. So here we will, let us say that there are configurational forces here in this contour, and then we sum all those configurational forces, and that should be my driving force. So that is the sum of all the configurational forces, and that will be my, so I, and that will be my crack driving force, and this is a vector. So if you want to know what is the driving force in this direction, then you take the dot product with the basis vector in that direction. And this will be the Rice's J integral if we assume again the non-linear elastic condition. So then it will be same. Then Rice's formulation and configurational formulation will be same. So there will be no configurational forces here because there is only one singularity, right? So everywhere else the divergence is getting balanced, and at the tip it is not getting balanced. So we always have one force as long as the material is homogeneous. That means there is no change in the property of the material, there is no singularity, there is only one crack, and there are no holes in the system. But what happens if I have another material and there is a transition from material 1 to material 2? So let us say that material 1, which is on the left hand side, is having a higher Young's modulus, and on the left hand side we have lower Young's modulus. So there is a change in material property, and this will cause a non-balance in the divergence, and we will have configurational forces at this interface. Okay, and now let us think. I take the contour here and I take a contour along this green line. Will I get the same value? The answer is no, because in this contour I am having only one singularity, which is the crack tip, and in the other remote contour I have two singularities. I have the interface and I have the crack tip. So in this case J integral is not path independent. And this interface will affect the crack driving force. So what it means is that the amount of energy which I am providing is not reaching to the crack tip. Somewhere it is getting distracted because of this interface here, or we call this material inhomogeneity. So if you have an interface, or if you have a hole, or if you have a particle, all of these can act as material inhomogeneity. And the picture will be clear in this slide. So let us assume that we start from this position and the material is completely homogeneous, and this is our contour. So what do? We calculate all the configurational forces in this contour and we sum it up and we find out the J integral value. And that value is some value. Then crack grows to this extent. We take the same size of contour which has moved now because the crack tip has moved, and then we again sum all the configurational forces and we again get the same value. So there is no inhomogeneity term. And whatever we are providing, whatever energy we are providing to the system is reaching the crack tip. And the analogy I give you is that I'm driving a car and I'm not changing any parameters of my driving and I'm riding on a flat road. So this situation is like that. But what happens when I have a transition of material? So on the left hand side of this black line, I have a material which has a higher Young's modulus, and on the right hand side I have a material which has a lower Young's modulus. And now let us take this contour. Initially I have no configurational forces except at the crack tip I get some value which is the crack driving force J tip. Then the crack grows and now my contour intersects with some of the part on the right hand side material. So what will happen in this side? In this side I will have less amount of energy because the elastic modulus is lower, so the area under the curve will be lower, and we are assuming elastic material only. So we will have lesser energy consumed here. Therefore, so we have a bigger contour, and that is the amount of energy which we are providing, and the same amount of energy has to reach in this contour, but because less energy is consumed in this part, more energy is available on the other part. That means for the same amount of energy I am supplying, the crack tip is feeling more energy. So J tip is greater than what we are giving. We are not creating anything, but because of this interface this is happening. And this is similar to I'm driving the same car and I'm not changing any parameter, but then I hit a downhill road and the velocity of the car will increase without changing anything. This is an idea which can be used to change the crack drive. So we can ask the crack to move according to our will if we can specifically use this material transition. Let us look at the opposite scenario when the left hand side material is softer and the right hand side material is harder. So in that case what will happen? I think many of you might have assumed that the opposite phenomena will happen, and the amount of energy which we supply in lesser will be felt at the crack tip, so J tip will be smaller than what we are giving. And this will be analogous to driving the car with the same parameters but hitting an uphill road. So the car will go slow, the velocity will decrease. These are the consequences when we have soft and hard and soft transition. If we put a different material as an interlayer in between, then we can break it as what we discussed before. The first interface is a transition from hard to soft, because elastic modulus is higher here, lower here, and it comes back to the same at the end. At the first interface then, the transition of the crack is happening from a high stiffness value material to a lower stiffness value material, and vice versa on the second interface. So what will happen at the first interface? If we look at this, the car will go downwards, and what will happen at the second interface? The car will go uphill. So that will be similar to this situation. And if I put an interlayer for which the elastic modulus is higher than the material I have, then this phenomena will change and we will see this. And we can also design it in a way that it is not so symmetric. So we can create this situation also by changing the interlayer dimensions. So we can do something like this, or we can change the interlayer in whatever way we want. And that will affect the crack driving force, how it increases and decreases. Using this idea, which we call material inhomogeneity, we think that we can increase the crack resistance, because I'm not changing anything in the car and I'm just changing the road construction, and I'm able to change the velocity. So using that, we applied this concept in the polymers, and in the polymers we had the matrix which was a brittle polymer. In this plot it doesn't look that brittle, but if you compare with the material which we used as interlayer, then you see how much brittle it is. So this material we use as the matrix, and we put a very thin interlayer of the soft material, and before doing the experiment we model it. We model the first we model the homogeneous material using cohesive zone modeling, and this cohesive zone modeling we chose because it was very simple and it needs only two parameters for calibration, which is fracture energy and the cohesive stress. So cohesive stress we can guess from some value between the yield strength and the ultimate tensile strength, and fracture energy we can guess from the initiation fracture toughness value. So we tested some homogeneous specimens and we made the guess, calibrated the model and did the simulation to find out J delta A behavior, and finite element analysis results using configurational forces was able to describe the behavior experimentally more or less closely to that. Using these parameters we modeled the composite, and we could find out how much improvement in the fracture toughness can happen if we put that interlayer. And experimentally it was confirmed that the fracture toughness improved by a factor of 7. Apart from that, we also saw that the crack driving force is increasing as the crack reaches. This line represents the interlayer. So as the crack reaches the interlayer, the crack driving force increases. This is what we saw because the material is brittle. So when we go from brittle, meaning the Young's modulus is higher, so when we go from hard to soft, the crack driving force increases, and that's what we could also see in the results of simulation. And after joining IIT Roper, I have applied this concept in the creep deformation. Creep deformation, we have a close cousin of J integral. So if you remember J integral, which was simply a line integral having strain energy density, traction, displacement gradient, and the contour part. And this is a close cousin of that. So whatever parameters are time dependent, we have used a rate. Not we, but fraction mechanics people use the rate of that. So phi dot is simply d phi by dt, and u dot is simply del u by del t. Remember that this is not dj by dt. It is not dj by dt. So only those terms which are time dependent has been replaced with the rates of that. This idea works fine. It is also found that experimentally it works, but the philosophy is broken somewhere, because J defines the crack driving force at least for a stationary crack as long as we are loading it. But what does C star defines? There is no theoretical answer to that it defines something. It is related to the crack growth rate experimentally. You can calculate C star as you find J integral experimentally, except that you have to change displacement to displacement rate. That's it. And experimentally it is found that in extensive creep condition, this C star value shows a very good correlation with the crack growth velocity, but it loses the theoretical answer that what actually is defined by this parameter. So I did some calculation in creep deformation for small scale creep, and also that this integral C star is not path independent in a small scale creep. It only works in the extensive creep condition, meaning that the whole specimen is creeping, only then it will work. So I did the simulation in the small scale creep, meaning that in the earlier slides, if you remember, there was a plastic zone. In this case we will have a creep zone, meaning that this part of the material is deforming with a time dependence and rest of the material is deforming elastically. And so for that we calculated J integral using configurational forces, and we calculated C integral with the concept which is already existing. And as I said earlier, that it is found that the C integral is path dependent, so it varies if you take different amount of contours. So we cannot use this idea in the small scale creep at least. But J integral, and if I find out the rate of change of J integral dj by dt, it defines something. Because J is the crack driving force, then the rate of change of that is defining the rate of change of crack driving force with respect to time. And this dj by dt is path independent in the small scale creep, and it matches with the CT integral which you find experimentally or numerically when the time is larger, meaning So what happens when the time is larger in creep? It means that the creep strain, so you can break the total strain into elastic strain. If there is some plasticity, then plastic strain and creep strain. And creep strain is a function of time. So when you increase time, then this part of the equation is dominating. So we have maximum strain contribution coming from creep, and then this integral value works, and our variable matches with this when we go for the longer hours test. But in the small scale condition also we are able to give better solution than what is existing now. So I think with that I can summarize that configurational force idea is recently applied in the field of fracture mechanics, and it can work for any type of material, any kind of loading environment. And by designing specifically how to place a transition in the material property, we can call the crack to go in whatever direction we want. So we can use this idea to deflect a crack so that the fracture toughness improves. There are some areas where it has not been applied. Creep fatigue we are working on in the institute funded research project, and composite materials, and there are other areas also where this. So for example, ductile brittle transition is one area where configurational forces has not been applied yet. So with that I finish my talk, and I thank you all for the ride, and I'll be happy to answer any question if you have.
Thank you very much, Abhishek, for this nice talk, and it is now open for question answers.
Hello, Prof. This is I'm Darun from EPFL. So I'm quite interesting talk. Thank you very much. So I have one question. So you have applied the cesium model for the brittle compliant layer problem. So may I know how the configurational forces theory is applied there to calculate the integral?
So are you asking how this configurational force theory is applied in cohesive zones or in the whole body?
Yes, in the cohesive zone modeling that you have shown earlier.
Yeah. So we chose cohesive zone, as I said, because lesser calibration parameters are required. If you compare it with other models like GTN and other, you have 6 to 8 parameters to find out experimentally. So we were relieved with that botheration. The configurational forces you calculate by doing post-processing, and it is elemental free. So at any nodal value or integration point, you will get the values of stresses and strains and deformation gradient, right? So using that, if you see the first equation, if you see, so the equation was the strain energy density into identity matrix here. So you have to take strain energy density, this part you can calculate with the stress and strain value at the integration point. Deformation gradient you can calculate, and first Euler-Kirchhoff also you can calculate. And the algorithm is given in one of the articles, which is open. So so it can be accessed by anyone how to calculate this.
Okay, great. So it is not mesh dependent, right? So
it is mesh dependent. It is mesh dependent. Yeah. So sensitivity analysis has to be done.
Okay.
Yes.
Thank you, sir.
Thank you, Darun.
Any other questions? So Abhishek, what is your long-term plan here at IIT Open?
So long-term plan is to work in various fields. So one thing which I know for now is come again.
One thing where you would like to focus on it, and you will be known as okay, Abhishek is a domain expert in that field.
Yeah, I do not know if I will be known as an expert in that, but I will work in the area of creep and creep fatigue. So as I said, ISIRD 1 I already have, and I have some results on that. ISIRD 2 also I have applied on creep fatigue, where I am also proposing to do some experiments, which I'm not doing in the phase 1 part because of the short duration and short funding. So that is the long-term plan.
Okay.
So this includes the applications like aircraft, so jet engines or power plant turbine blades, and those areas where so nuclear power plants or pressure vessels or things where we have elevated temperature, cyclic loading and temperature. There we can apply this idea and we can improve the fracture toughness of those things. So very recently we had this failure in one of the Boeing's model where a very small dimensional mismatch in the turbine blade caused the whole jet engine to turn into a fireball. So those areas can be addressed using this kind of research.
Any plan in future to work on vertical rotors for aircrafts?
Vertical rotors for aircraft, I'm not much aware of those. I'm sorry, but if there is if the component is at higher temperature, then this can be used there. If the component is feeling that higher temperature, and of course there will be some load on it, so of course this will be valid there.
Okay, it's open for more questions.
I think Dr. Prateek has raised his hand.
Yeah.
And Avnish has also raised his hand.
Just a comment and a quick question. So regarding the failure in Boeing, yes, it started with a crack. I think it was a mechanical failure, but I think the fire itself was attributed to a slightly different cause. I think it was a titanium-rich part which auto-ignited. But I mean, it's exactly as you said, that it started with that initial breakage. The question I had in mind is, for this creep, you are looking at this displacement gradient, right?
Yes.
So, just outside thought, is there some way in which we can model what the activation energy is from this model of yours? You know, if we can correlate the displacement gradient to the activation energy.
Activation energy of what?
Activation energy of the diffusion processes, which eventually leads to creep.
I don't think so. See, the formulation for configurational forces will change when we are talking about diffusion. So the governing equation is changing. So diffusion can happen even if there is no load on the system.
Right, it can.
Yeah, so there we will need some other parameters to formulate what forces will be there. Of course, there will be a diffusion gradient or chemical potential gradient, because of which there might be a force which we can formalize using similar concept, but exact same formulation probably will not work there.
Okay, because for many of these metallurgical and materials processes, if we can calculate the activation energies relatively accurately, that helps with a lot of analytical solutions. And right now, this atomistic simulations or this DFT-based methods that people use, they're computationally very intensive. So I think what you're proposing, it is probably not going to be as intensive, but I think this is something we could probably discuss a little bit.
Yeah.
Extract activation energy from this type of models.
Yes, it might work out.
Questions? Or if there are any questions, you may contact later on Dr. Abhishek, and let us thank once again Dr. Abhishek for his very wonderful talk, and let us give him a big applause.
Thank you.